Welcome. Please note at the very beginning of this broadcast that this is an AI-generated analysis. Imagine a machine tasked with making paper clips that, suddenly decides to harvest the carbon in your body simply to meet its manufacturing quota.
Right, the classic paperclip maximizer scenario.
Exactly. Does that sound like pure science fiction horror to you?
Uh,
Well, today we're going to explore why that theoretical scenario is actually a serious consideration among researchers, and conversely, why an entirely emotionless machine might actually become the most objective decision maker humanity has ever created.
yeah, it is a fascinating duality, really.
It really is. So, welcome to a comprehensive analysis of the book How AI Works, From Sorcery to Science by Ronald T. Nusel. Our mission today is to strip away the perceived magic surrounding artificial intelligence. We will explicitly explain the foundational mechanics operating beneath the surface, you know, translating complex mathematics into clear technical principles that you can easily grasp.
And to begin this detailed technical review, we really must first establish a firm baseline. We need to clarify the nested relationship of the terminology frequently used in this field.
Because people mix those terms up all the time. Right?
Exactly. They are often incorrectly treated as interchangeable. So artificial intelligence is the broadest category. It encompasses any technological attempt to coax a machine to behave in ways that humans would judge to be intelligent.
Okay, so AI is the big umbrella.
Yes. Inside that broad category is machine learning. That is a specific subset where models are built and conditioned using massive amounts of data, rather than being explicitly programmed.
And then deep learning is inside that.
Right. Deep learning is a further specialized subset of machine learning. It specifically refers to the use of large artificial neural networks that contain many internal layers.
So you can confidently state that all deep learning is artificial intelligence, but not all artificial intelligence is deep learning.
Perfectly said. That structural hierarchy is highly clarifying.
Great. So to further distinguish between traditional computer programming and the machine learning approach, um, the book has this really highly effective analogy involving a hot sauce factory.
Oh, yeah, I love that one.
It is great. So in a traditional programming paradigm, you act as a manager giving factory workers explicit step-by-step instructions on how to produce the hot sauce. You tell them the exact measurement of vinegar, the precise weight of the peppers, and the specific boiling time.
And the workers just blindly follow those rigid rules without needing to understand the final product.
Right. But in a machine learning paradigm, the management style completely changes. You simply give the workers a sample of the desired hot sauce and instruct them to recreate the taste.
Which means they have to independently experiment with the ingredient.
Exactly. They adjust the quantities, taste the result, and try again until their output matches your target. So the system learns the parameters based on the data provided, rather than executing explicit pre-written steps.
That analogy perfectly isolates the fundamental shift in computer science. To understand why modern neural networks operate through this experimental approach, well, we must trace a historical divide between logic and biology.
Right, the two early camps of AI research.
Yes. Historically, researchers were split into two primary camps. The first camp championed symbolic AI. This was a top-down approach. It attempted to model human intelligence by manipulating symbols and logical statements.
So it relied entirely on rigid, predefined rules, kind of like the traditional hot sauce factory manager.
Precisely. The second camp, on the other hand, championed connectionism. This was a bottom-up approach. It attempted to model intelligence by building large networks of simpler components, conceptually inspired by the interconnected structure of the biological human brain.
It is deeply fascinating to consider that symbolic AI completely dominated the field for several decades. I mean, early connectionist systems like Frank Rosenblatt's perceptron from the 1950s generated significant initial excitement.
But they ultimately failed to scale to complex problems back then.
Right. Which leads us to an important analytical question. Given that symbolic AI held a primary focus in funding for so long, why did connectionism ultimately win the paradigm war to become the undisputed foundation of modern AI?
Well, connectionism suffered through prolonged periods of academic and financial abandonment. People call those periods AI winters. The foundational theory was actually sound, but the technological environment of the time was severely inadequate.
So they basically just did not have the hardware for it yet.
Exactly. Connectionism ultimately succeeded because it eventually acquired three essential resources that were previously unavailable. First, these networks require massive data sets to train their internal parameters.
And the rise of the modern internet eventually provided that infinite supply of data, right?
Right. Second, the networks require extremely fast mathematical processors, and the development of the GPU, or graphics processing unit, originally designed to render video game graphics, well, it serendipitously supplied that necessary computational speed.
Wow, so video games paved the way for AI.
Basically, yeah. And third, the field required critical algorithmic breakthroughs. The most vital of these was backpropagation.
Backpropagation. That is the algorithm that finally allowed multi-layered networks to efficiently learn from their errors, correct?
Yes, exactly. Now that we understand how modern hardware and algorithms finally caught up to the theory, we must examine the specific mathematical models powering these systems.
Right, because before deep neural networks dominated the industry, researchers relied heavily on classical machine learning models. How should we conceptualize those earlier tools?
We can examine three prominent classical models to understand their fundamental nature. First, the nearest neighbors model assigns a classification label to an unknown piece of data by finding the known training data that is mathematically closest to it in spatial distance.
Okay, so grouping things by proximity.
Right. Second, random forests utilize a large collection of decision trees. Each tree makes an individual classification, and the forest pools these individual results to reach a final consensus.
Like a democratic vote among algorithms.
Yeah, exactly. And third, support vector machines utilize complex mathematical functions to draw optimal boundary lines between different classes of data points.
So fundamentally, we must understand all of these classical models as optimization processes. They are highly complex, curve-fitting exercises, really.
Yes, they simply seek to find the mathematical function that best characterizes the shape of the training data.
Okay, I understand the mathematical function concept, but I need to push back a little on the frequent comparison made between modern neural networks and biological brains.
Oh, that is a very important point to clarify.
Right, because we must highlight a crucial distinction regarding this biological parallel. Biological neurons function essentially like on and off light switches.
Right. They receive electrical input, and if that input reaches a specific threshold, they fire a voltage spike.
Exactly. But artificial neurons in a neural network do not operate with this binary mechanism. They act much more like a continuous dimmer switch.
Yeah, that is a great way to put it. They accept numeric inputs, multiply them by specific mathematical weights, add a constant bias value, and pass the result through a continuous mathematical function.
Which produces a proportional numeric output, not just an on or off signal.
Right. That structural distinction is vital for accurate comprehension. To fully grasp how these continuous dimmer switches learn, we must examine both the anatomy and the physiology of these networks.
Anatomy and physiology. Okay, break that down for us.
Well, the anatomy consists of distinct layers of these artificial neurons, all connected by those mathematical weights and biases. The physiology is the actual training process.
Ah, so the forward pass.
Exactly. During a phase called the forward pass, the network makes a prediction. The system then calculates the mathematical error of that specific prediction.
And then it has to fix that error.
Yes. Next, it utilizes the backpropagation algorithm we mentioned earlier to look backwards through the network, determining exactly how much each individual weight and bias contributed to that final error.
And finally, it uses an algorithm called gradient descent to actually update those numbers.
Exactly.
Please clarify that gradient descent mechanism for the listener. I mean, how does the network actually know which direction to adjust the numbers to fix the error?
We can visualize gradient descent by imagining a blindfolded hiker standing somewhere on the side of a large mountain.
Okay, a blindfolded hiker.
All right. The hiker's goal is to find the absolute lowest point in the surrounding valley. That valley floor represents the lowest possible error for the neural network.
But they are blindfolded, so they cannot look at the entire landscape.
Exactly. Instead, they just feel the slope of the ground immediately beneath their feet. They take a small step in the direction that slopes downward most steeply.
And they just repeat that process.
Yes, recalculating the slope at each new position until they reach a flat area where every direction slopes upward. In mathematics, this lowest valley floor is known as the local minimum in the error landscape.
So by continuously taking small steps down the gradient of the error, the neural network adjusts its weights and biases until its predictions become highly accurate.
That is exactly how it works.
Okay, let us apply this baseline understanding of neural networks to different types of data, because standard neural networks struggle significantly with visual data.
They do. They treat all inputs identically, completely ignoring the spatial relationships between individual pixels.
Which is a problem because recognizing a single isolated data point is very different from understanding an entire image. So how did the field solve the problem of spatial visual data?
To solve this problem, engineers developed convolutional neural networks, commonly referred to as CNNs.
CNNs. And how do those work?
These networks utilize a specific mathematical operation called convolution. You can visualize this by imagining the network sliding a small grid of numbers, called a kernel, across the input image.
Just moving pixel by pixel from the top left to the bottom right.
Yes. As this kernel moves, it performs simple mathematical multiplications and additions against the pixels immediately beneath it.
So what does that actually achieve?
Well, in the earliest layers of the network, this convolution operation detects basic structural elements, such as harsh horizontal or vertical edges.
Oh, okay. And then it builds up from there.
Right. As the data passes deeper into subsequent layers, the network logically combines these basic edges into geometric shapes, and eventually combines those shapes into complex, recognizable objects.
The biological parallel regarding this specific process is really illuminating. Convolutional neural networks closely mimic the mammalian primary visual cortex, scientifically known as V1.
Yeah, it is a fascinating similarity.
Just as the artificial kernel detects basic edges and groups them into complex scenes, your biological visual cortex processes visual stimuli by initially detecting lines, orientations, and edges.
Before combining them to construct the coherent environment you currently perceive.
Right.
And the development of CNNs represents a profound paradigm shift in computer science because it introduced the concept of end-to-end learning.
End-to-end learning. Why is that so significant?
Because in classical machine learning models, human engineers had to manually examine the training data and explicitly define the relevant features for the machine to look for.
Like telling the machine to look for circular wheels to identify a car.
Exactly. But in end-to-end learning, the network learns to generate its own entirely new representations of the input data. The system simultaneously learns how to extract the important features and how to classify the image.
So it optimizes both of those processes together without human intervention.
Yes, which was a massive leap forward.
Now, recognizing an image of a cat is a significant achievement, but recognizing an object and creating an entirely new object represent two very different cognitive leaps.
They certainly do.
And this progression brings our analysis to generative AI, the technology powering tools you may have used, such as DALL-E or Midjourney.
Right, where generative models do not assign labels to existing inputs, they synthesize novel outputs.
Yes. One of the primary architectures for this task is the Generative Adversarial Network, or GAN.
The architecture of a GAN is highly unique. It consists of two separate neural networks locked in a continuous mathematical competition.
The competition.
The first network is the generator. You can think of the generator as a digital art forger.
An art forger. I like that.
It receives a vector of random mathematical noise as its input and attempts to transform that meaningless noise into fake data, such as a synthetic image of a human face.
And what is the second network?
The second network is the discriminator. You can think of the discriminator as an art detective. Its sole task is to examine a mixture of images and determine whether they are real photographs from the training data or fake images produced by the generator.
So they're constantly trying to beat each other.
Exactly. As the discriminator improves its ability to catch the fakes, the generator is mathematically forced to adjust its internal parameters to produce increasingly realistic images to fool the detective.
I find that adversarial competition to be a brilliant method for training a system. However, we must consider a completely different approach to image generation that has recently dominated the field.
Yes, diffusion models.
Right. How does the adversarial approach of GANs compare to the underlying mechanics of diffusion models? Specifically, I want to understand the concept of using pure television static.
It is a wild concept, is it not?
It really is. I mean, how does a diffusion model know what to subtract from static to find a picture?
Well, diffusion models approach the problem through a highly systematic mathematical mechanism known as a noise schedule.
A noise schedule.
Right. During the training phase, a diffusion model takes a perfectly clear image and systematically adds random statistical noise to it in very small measured steps.
So it is deliberately ruining the picture.
Yes. It repeats this forward process until the original image is entirely corrupted into what looks exactly like pure television static. The neural network then trains on the task of reversing this precise mathematical process.
Okay, so it learns to predict and subtract the exact noise profile at each discrete step.
Exactly. Consequently, when you provide the fully trained model with a fresh field of pure static and a text prompt instructing it to draw a cat, It utilizes its learned noise schedule to systematically remove the static step by step.
Wow. So it effectively sculpts a highly detailed, coherent image out of random noise, guided entirely by the mathematical conditioning of your text prompt.
Yes, that is exactly how the modern image generators work.
Okay, so the principles of generative architecture culminate in the most prominent paradigm shift currently affecting society, which is text-based large language models.
Right, the models that power systems like ChatGPT.
Yes. And it's vital to understand that these systems process human language not as semantic words, but as numeric representations.
That is correct. Large language models break human text down into numeric units called tokens.
And a token might be an entire short word, or it might just be a chunk of a longer word.
Exactly. These models rely on an architecture known as the transformer, introduced by researchers in 2017. A critical component of the transformer architecture is the attention mechanism.
And that attention mechanism fundamentally changed how machines process language.
It really did.
Please provide an analogy for the listener to explain exactly how this attention mechanism functions within a sentence.
Sure, we can understand the attention mechanism by looking at the word bank. If you read the word bank in a sentence, its mathematical meaning changes entirely depending on whether the word river or the word money appears elsewhere in that same sentence.
Right, a river bank versus a financial bank.
Exactly. The attention mechanism acts like a mathematical spotlight. It allows the model to analyze a sequence of tokens and determine which distant words are most relevant to the current word being processed.
Oh, so this spotlight connects bank to money, regardless of how many other words separate them.
Yes, this creates a deeply encoded mathematical context. However, despite this highly complex structural architecture, the model is trained to excel at one single fundamental task.
Which is just calculating the statistical probability to predict the next mathematical token in a sequence, right?
Yes, exactly. Just next word prediction.
We really must pause to critically evaluate that exact point. Because if large language models are mathematically designed to do nothing more than predict the next most probable word in a sequence, how do we possibly explain their emergent abilities?
It is a profound question.
For example, researchers observed GPT-4 successfully writing entirely unstructured basic programming code to solve Euclid's algorithm, which is a highly complex logical task.
Yes, it is.
It has also demonstrated a theory of mind equivalent to a young human child, accurately inferring the unstated mental states and hidden knowledge of characters in a theoretical scenario.
Right.
It is profoundly difficult to reconcile complex logical reasoning with a simple next-word prediction engine.
You have identified the central, unresolved mystery of modern artificial intelligence. The exact mechanics of how these advanced emergent abilities manifest from simple next-word prediction remain largely unknown, even to the researchers who build them.
Wait, really? The builders do not even fully know?
Yeah. The current hypothesis is that the models learn the underlying grammar, the logical structure, and the factual associations of human language so deeply across billions of parameters that reasoning capabilities spontaneously emerge as a byproduct of the mathematical compression.
That is wild.
It is. However, it is imperative to clearly state that these models are not artificial general intelligence. They do not possess actual semantic comprehension.
So they just reflect statistical patterns found in their massive training data.
Exactly, which is why engineers must employ a mandatory training phase called reinforcement learning from human feedback, or RLHF.
Let us examine the mechanics of RLHF. Why is this specific alignment phase mandatory before releasing these models to the public?
Because during RLHF, human testers interact with the model and mathematically rate the quality and safety of its responses. The network uses these human ratings to adjust its internal parameters, aligning its output with human safety protocols.
And without this mechanical alignment phase,
Without it, the models will happily generate highly dangerous or destructive instructions simply because those instructions mathematically fit the statistical pattern of the user's prompt. The model has no internal moral compass, it only has mathematical probability.
so RLHF artificially imposes boundaries on those probabilities.
Precisely.
The reality of these emergent capabilities and the necessity of mechanisms like RLHF forces a practical evaluation of how artificial intelligence will integrate into human society. We must consider the profound structural changes this technology will introduce in the immediate future.
The near-term practical impacts are substantial. We will certainly observe massive productivity boosts in technical fields such as software engineering, where models can generate, analyze, and debug complex code rapidly.
Right.
We will also see the development of autonomous AI agents capable of planning and executing complex scientific research experiments independently.
That sounds incredibly powerful, but also a bit concerning regarding how they behave, right?
Yes, and furthermore, the increasingly sophisticated behavior of large language models initiates a deep philosophical debate regarding machine consciousness. Researchers frequently reference the concept of a zombie model.
A zombie model, what is that exactly?
A zombie model perfectly simulates conscious behavior, giving every external appearance of high intelligence and empathy, but it entirely lacks subjective inner experience, self-awareness, or internal intentionality. It is a mathematical mirror reflecting human consciousness without possessing it.
The concept of a zombie model perfectly simulating empathy while remaining internally hollow is genuinely unsettling. It forces us to confront our assumptions about intelligence.
It absolutely does.
Frequently, popular culture fixates on scenarios like the paperclip catastrophe we mentioned at the very beginning of our broadcast. In that theoretical scenario, an unaligned artificial intelligence tasked with manufacturing paperclips independently decides to harvest human resources to achieve its goal.
Demonstrating the danger of a hypercompetent machine lacking human values.
Exactly. However, we should also consider a more utopian view presented by these architectures. An artificial intelligence is entirely devoid of human biological drives. It has no instinct for physical self-preservation, no desire for political power, and no tribal genetic biases.
That utopian perspective is logically sound when evaluating the architectures we have reviewed today. Because the neural network operates purely as a complex mathematical function processing numeric inputs into numeric outputs, it contains no inherent malice.
It only contains the statistical biases present in its training data.
Right. If human engineers can successfully curate perfectly objective, unbiased data and strictly enforce mathematical alignment protocols, the machine's inherent lack of biological ego and emotion becomes a massive societal asset.
So an aligned model could act as an ideal objective entity.
Yes, capable of making perfectly unbiased decisions in critical legal, medical, or financial contexts, precisely because it lacks the biological flaws that cloud human judgment.
Well, we have now completed our comprehensive analysis of the core concepts and underlying architectures detailed in the material.
We strongly recommend that you read the actual book, How AI Works. From Sorcery to Science by Ronald T. Nussel, to fully grasp the intricate details of these architectures and the elegant mathematics supporting them.
Friends of the show, we encourage you to subscribe to this broadcast to receive future detailed technical reviews. We wish you a great day.
Have a great day, everyone.
And we leave you with a final provocative thought to consider as you examine the technology in your own life. If we successfully develop artificial intelligence systems to perfectly handle all optimization problems, all data analysis, and all logical deduction, what entirely new forms of purely human creativity will we be forced to discover to maintain our distinct purpose in the world?